Good afternoon, everyone. Myself Shuma. I'm geotechnical engineer at Intermoor. So my role basically focuses on anchors and any stuff which goes on seabed. So basically, I deal with structures which goes on seabed and also below seabed. So today I'll be talking on SEPLA and FEPLA, both plate anchors, but uses different installation technology and different followers. So combining both, a plate anchors can be installed in almost any kind of seabed. So today I'll be walk you through brief company description, then all available mooring anchors in the present day and their limitations, and I'll be introducing the concept of SEPLA, FEPLA, and focus more on the FEPLA installation sequence, cost benefits, and the development status. So at Intermoor, we provide end-to-end mooring solutions starting from engineering, design, products, offshore installations, inspection, and decommissioning. Our track record involves projects and all different types from renewables, wind turbine, foundations, moorings, drilling campus, decommissioning over 100 plus locations across the globe. So when we talk about anchors, the first ever anchors used is a dead weight or a huge weight of stones. So, but for today's mooring, where for a dead weight anchor, we need more submerged weight than the load itself. So for today's modern day mooring, the dead weight anchors becomes quite challenging, which comes to the next category, which are the piles. So in this figure, number 4, 5, 6, and 7 are piles. Number 4 is a suction pile, which is used for an anchor and also offshore foundation. So it's a hollow cylinder, first lowered in the seabed, let it penetrate by its self-weight. Then water is pumped out of the can, which creates a pressure difference, and it drives the anchor inside the seabed. Works extremely well for soft clay seabed, but it becomes challenging if we have layered soil or hard soil or sand over clay, where there can be refusal. The next category, number 5, is a driven pile, which can be used for any type of seabed where there is layers of seabed, hard seabed, but it becomes very huge in terms of steel, in terms of installation and stuff, and we need complex installation. And the number 6 is a drilled and grouted pile, which is kind of a good solution if we have rock or something very hard where we cannot use any other type of pile. And the number 7 is a torpedo pile, which is kind of installed by self-penetration, so which works only for clay type of seabed. So combining different types, pile can be used as an anchors, and pile has a good positional accuracy, means you can install the anchor exactly where you need. But it's not an efficient anchor, because when loaded, say it is loaded in the left side, the most of the surface area of a pile is not in use. It's not an efficient way of anchoring, which comes to the first 1, 2, and 3, which are number 3 is a drag anchor, number 2 is a drag embedded plate anchor, and number 1 is a driven plate anchor. So a drag anchor, we know, is what's very good for temporary moorings and also in some cases permanent moorings, but it struggle in its way of its installation. So it's installed by dragging in the seabed, and the property of the seabed changes as you drag along. So it is almost impossible to predict accurately what will be the drag of an anchor and where it will exactly end up. So, and also it's weak in uplift. So if it is a clay seabed, it can be installed deep enough, it can take some amount of uplift, but is a hard seabed where the anchor is not going inside the seabed. If there is an uplift, the anchor struggle in that case. So, and which comes to the next category, which can take uplift, is a drag embedded plate anchor, but it still struggle in the positional accuracy. If I don't have tolerance where I can adjust where the anchor end up, then drag anchor kind of struggles. Which comes to the final type of anchor, final type of plate anchors, or number one in this figure, which is a plate anchor. If it can be driven in a required depth, it can kind of solve the problems. So it is very efficient in a way. The entire area of the plate is providing the resistance, but the main challenge is how we put it inside the seabed. So I'll focus mostly on the plate anchors today, and I'll try to explain how it can be installed inside different type of seabed. So first, let's look at the scale of the anchors. How big can be for a typical 1,000-ton load? How big can be a gravity anchors? Then next is a driven pile, then suction anchor, drilled and grouted pile, and then the plate anchors. The reason, as I told, the pile sizes are so bigger because when it's loaded, the most of the surface area is not working. It's just there in the seabed. But when a plate anchors is loaded, the way it mobilized capacity, the whole plate is providing the resistance inside the seabed. So let's talk about SEPLA. SEPLA stands for suction embedded plate anchors. So it is the most efficient anchor when if it can be installed in its required space. And the concept is not new. US Navy has installed small plate anchors since 90s, 80s, and then Intermoor developed its own technology, SEPLA. And since 1990s, we have installed over 180 installations, which include 6 permanent mooring. And it is widely accepted by certification agencies like ASB and ABS and DNV. So let's take a small video how it is actually installed inside seabed. So SEPLA is basically a plate anchor attached below a suction pile. So just like suction pile, it is first lowered into the seabed, let it self-penetrate by itself weight, and the rest is installed using suction. So the water is pumped out of the pile, which makes a pressure difference, and it drives the anchor inside the seabed. And after installation, the follower is taken out, and then the anchor is keyed or rotated in a way the anchor is perpendicular to the loading line. So once the anchor reaches this position, the anchor will not move. So when you compare to a drag anchor, the way it installed, if you pull, it will keep on moving unless you proof load it to a load, and later on you see the load which is less than the proof load. So once you install a plate anchors and it is keyed, it will not move. So it's not needed to be proof loaded. So moving forward, so if it can be installed, it will serve as good as a suction pile. And since there are saving in terms of steel making and vessel transit, so this photo shows, diagram shows the jumbo flare plate is loaded with 18 SEPLAs. And combining steel making, vessel transit, there are opportunity to save as much as 47%. This example is for 16-line mooring FPSOs. So first, let's look how the anchor is keyed, and this is a real experiment which was done in University of Western Australia. So after the anchoring installed, so this is a sand bed which used some pigment to show the behavior of the soil inside the tank. Play the video. If you can play the video. Video don't play. Yeah, just a play button, please. Thanks. So, yeah, so this is the keying process of the anchor. So, so once the anchor is keyed and it is pulled, as you can see, if it can be installed inside the seabed deep enough, the soil around the anchor is only contributing to the capacity of the anchor, and which is called a deep failure mechanism. Means the anchor can be installed 4 times or 5 times the width of the anchor. Then there will be a deep failure mechanism which is kind of surrounding the anchor, and what happens in the seabed, the anchor is kind of less affected by that. Yeah. So as is installed using suction, so it comes with an inherent problem of suction piles. So if we have again hard seabed or layer seabed or sand over clay type seabed, so where the suction embedment itself fails, then their SEPLA will also struggle to install because when the way the suction pile installed in sand is the water is pumped through the wall and that kind of drives the anchor. If there is any impermeable layer in the seabed, that will stop that process. And also if there is any hard layer, it will struggle to be installed. Also the way the industry is shifting, especially for floating wind, shifting towards more semi-taut and taut mooring, where significant uplift is coming in the system. So, and it will see hard seabed or sandy kind of seabed, challenging seabed conditions. So it drives to develop an anchor which can be installed in almost any type of seabed, and which can also take uplift and for higher loads where proof loading a drag anchor becomes very challenging. So which comes to the development of FEPLA. So FEPLA stand for flexibly embedded plate anchors. So it can be installed in almost any type of soil. So it is a SEPLA or the same type of plate anchors, but it uses a different followers which combines a vibration motor and a impact hammer. So combining this vibration and impact hammer, we can drive this anchor in almost any kind of seabed. So let's take a closer look at the follower. So the follower has a impact hammer, vibro hammer at the top, and then a impact hammer embedded inside the follower. So the vibration, if there is a sandy seabed, using vibration, the anchor can be installed very easily in sand. But then at some depth, if there is a hard layer, then the impact hammer will take over and it will drive the anchor to the required depth. And we are developing the technology with our Actian group companies 2H and Menk. 2H has completed a drivability analysis. So we found that a 320 kg vibro hammer and 270 kilojoule impact hammer, which is by the way much smaller than we need for a driven pile, so is kind of sufficient for almost any type of soil. And the installation driving time can be as low as 20 minutes. Let's look at the size of the plates. So for normal clay, typical 1,000-ton seabed tension, which is kind of very high tension. So it can be 60 meters square, as big as 60 meters square in normal clay. But in medium sand, where the soil is favorable, it can be as small as a 12 meter square plate. But when you compare the estimate weights to the equivalent pile, the weight every time is 3-4 times smaller. So the steel required is 3-4 times smaller than piles. So let's look at the installation sequence. So first, the anchor is loaded with its tool. So it's a typical example where a 105 meter edge is loaded with 21 anchors. Then it's lifted and lowered to the seabed, lowered to the water using crane or stern roller. Then first, as I told, it's installed by vibration, and then if we reach a clay layer or hard layer, we use the impact hammer, and then after installing, the tool is then recovered using vibration again. Then the mooring line can be terminated or buoyed off or pre-laid on the seabed. So let's also see what are the cost benefits. So we typically compared with 30 floating offshore wind, and we compared with driven piles. So if for 10-degree uplift, there is an opportunity to save from 29 to 33%. But when the uplift angle is more, the savings becomes more prominent, because driven pile is kind of when you have 45-degree uplift with 1,000 ton tension, the size of driven pile becomes very, very huge. Also, it's a plate, so it's a very simple fabrication. So you open door for more fabricators, which again saves lot. The savings is not only in terms of money, but also in terms of carbon emissions, and it's more prominent. We can save as high as 81% where the soil is favorable. The minimum saving is 67% in terms of carbon emission. That's just because we need much, much less steel than a pile. When we compare to drag anchor, in terms of when I have 1,000 ton tension for 3-line, 4-line mooring system, the installation cost is even 20 to 35% lower than drag anchors, and that's because for drag anchors need to be proof loaded, and with reaction anchor and tensioner for a high load. That's where the FEPLA becomes efficient, and it don't need to be proof loaded. Once installed, it will just be there. So it's a typical client's value where for a 60 hulls and 240 anchors in California, there was an opportunity to save around 45% in terms of anchor fabrication and vessel transit. So I'll finish with a status update. We have completed our pre-FEED study where 2H has completed the drivability analysis and published its book 2025. And then we also conducted 1G test in University of Dundee, where we used a model anchor with a model follower, and we have used vibration to drive the anchor, and then we used a loading frame to push the race. So I have this video. So at the back screen, actually, where it shows the kind of response, load response. So this part is being installed using vibration. And after that, when the graph will take the peak, so at this point, when the load start increasing, that means it's being pushed by the loading frame. So one thing we seen from this study is when you install in loose sand, due to the vibration, the loose sand even densifies and gives more, the capacity even increases more in the loose sand. We are also participating in linkage project with Australian Research Council, then Seacore centrifuge test, and Canada looked at the pull-out capacity of plate anchors in general in sand. And we expect initial prototype schedule for deployment by 2027. So that's all I have. Thank you. I'll like to open the floor for any questions.
Thanks, Shuma. That was really good. Thank you very much. Have we got any questions in the room?
Okay.
One at the back. Kieran.
Thank you for your presentation. I was wondering, for the decommissioning of the SEPLA, how would you recover the plate anchor itself?
So there can be sling. which can be kept on the seabed and which can be used later to decommission the anchor.
Okay. And also for the FEPLA, after it's driven with a vibro hammer,
Yeah.
How do you disconnect?
Yeah,
the
so
tight anchor?
there is a clamp, and that clamp is will be disconnected. So that is the thing which we are working on right now. So that is a challenging portion, and so there is a clamp which will be holding the anchor, and after the installation will be disconnecting using the clamp and taking out the follower.
Thank you very much.
Yeah.
Excellent. And the keying
Yeah.
of the anchor, what do you see in terms of load requirements versus trying to achieve an inverse catenary or proof loading?
So when keying, the anchor is is installed vertical, and then it is kind of rotated. So it's the load required is much less than the capacity.
Yeah.
So yeah, and it will vary depending on the soil, depending on the depth, depending on. But it's kind of rotating the anchor, not moving. So
Yeah.
it is much less.
Do you know, in the example with the fair player, the jumbo installation, did they key the anchor using that vessel, or did they have a
No.
anchor handling vessel?
No, so that's not an anchor handling vessel. So when installing anchor, you will need a HV to key the
Yeah,
anchor.
so they would have to follow up
Yeah,
that
they'll
with
have
an
to
anchor
follow,
handling.
with the HV, yeah.
Okay, excellent.